Okay, we're live. We're gonna continue the probability practice that I was doing yesterday. I didn't have time in the evening, so we're going to resume now. And let's go back to the chess tournament. So I think I did the chess tournament, but I'm gonna try and see if I can solve this on my own, without trying to remember what I learned, just like to see if like my neurons got reinforced. So we have not a round robin, but a knockout style tournament, and when two players meet, the player with the better skill. Oh, okay. I don't think I solved this actually. So this was where we were at. And what is the probability that players 1 and 2 meet in the final? So we have randomly drawn. Alright, so 1 will always win, so 1 will always make it to the final. But 2 most likely will win to the final, because anyone you confront except with 1, you will win, right? So the question is like, what's the probability of like 1 and 2 meeting in the final? Is just like, that's equal to the probability of 1 and 2 not meeting at all, right? And how hard is that probability to encounter? And how many rounds we have? We have, I think, n rounds, right? Right. If there are 2 to the n players, then there are n rounds. So you need n minus 1 rounds where and 2 doesn't meet. Okay, so how do we compute this? Like if n is 0, if n is 1, then the probability is like 100%. If n is 2, the probability is what? If there are 4 players, 1 and 2 won't meet if, right? There's only 1 round, so if 2 can run into 3, this is 3, or 2 versus 4, 1. So there's actually a 2-thirds probability, because this first round you have basically 3 options, and then by like, can you just ignore 3 versus whatever? Because that's like double. If 2 versus 3, then you can automatically infer the 1 versus 2. So like, this fully determines the other case. So you have 2 out of 3. But more generally, in the first round, there are 2 to the n players, right? And if we're looking, let's say we're looking at player 1, what's the probability that we run into player 2? It's going to be 1 out of 2 to the n minus 2, right? Because we're excluding ourselves and we're excluding 2. Or sorry. Out of the 2 to the n minus 1 players, we have a 1 chance. Or essentially it's 2 to the n minus 2, right? That's like from round 1. And then round 2 is going to be 2 to the n. So half the players are gone. And we subtract ourselves, and we subtract like that. So you multiply these together. And then 2 to the n minus 2 minus 2 and minus 2 minus 1, until you have 2 to the 0 minus 2, 2 to the, I guess it'd be 2 to the 1. If n is 1, two, 4 minus 2, that's the probability of you not running into 2. So if there are 2 rounds, the probability is like 4 minus 2 is 2. Wait. 3/4. Wait. 2 and 4 minus 3. Yeah, okay. Okay, I was tripping. Times, if it's 1, then it's 0. Till n. No. So n minus k is equal to 2. And the reason for that is we have 2 to the n minus 1 is equal because we want there to be 4 players, right? When there's 2 players, that's the last round. In which case this like equation would not make sense, right? So can we simplify this? I mean, so this is my answer. 2 to the 2 minus 2. So if n is 2, then you just compute it once. If n is 3, you compute it until this. I guess like this. Does this cancel out? Does this cancel out with this? And then this cancels out with this. And so there are n minus 1. Yeah, like that. That's my answer. Which is what they computed. And so they're Okay, I'm okay. Uh, Now let's go on to the counting approach. Because this is basically what we did. This is like intuitively the easiest way you compute conditional probabilities. But there might be an easier way to do this. This is probably 1 and 2 are in different subgroups. Let's assume that 1 is in a particular subgroup. What's the probability that 2 is in this subgroup? Well, out of all of these numbers, it has to be one of these 2 to the n minus 1 numbers. Over yeah. Okay, this is way easier. I can't explain it. It's just a different way of visualizing the problem. Okay, I can see it. So essentially, we can imagine like if you have your tree, right? For them to make it to the final, 1 and 2 must be in different subgroups. So you can draw like this, right? So what is the probability that 2 is in this like 1 and 2 are in different subgroups? Well, there are like, excluding 1, there are 2 to the n minus 1 different players. And for 2 to be in this bracket, right, it has to be among one of these. In each of these, there are 2 to the n minus 1. So it's simply 2 to the n minus 1 over 2 to the n minus 1 like that. There's a total number of players, excluding 1. And we need to exclude 1 here because 2 cannot be in the slot of 1, right? We're just looking at, there are like 2 to n minus 1 possible positions you can assume for 2, right? And you have 2 to n minus 1 different positions. Okay, yeah. So that's way easier than what I was doing. Okay, next problem. Application letters. I'm sending job applications to 5 firms. Okay. Morgan Stanley. Okay, you have 5 cover letters. All 5 cover letters are mailed to the wrong firms. well, what is the probability that it's melted right firm? So 1 out of 5 times like order matters, right? These are just 1 minuses with that loss of generality. And here, like, I assume a fixed ordering, 1 out of 5. Okay, so just 1 minus that. So isn't it just 1 over 1 minus 1 over 5 factorial? Is this 19 over 30? No. Why is this wrong? Okay, it's wrong because 1 minus this gives the probability at least one of them is wrong. But it doesn't give us the probability that all of them are wrong. So if you want them for all of them to be wrong, we need to say well, each event you have 1 out of 5, I think, right? Can you say that? Like, hmm. this is 1 minus 1 minus A and B. Wait, is this 1 over 5? P of AB is equal to P of A given B, PB, right? So A and B, if it's A conditioned on B, okay, this is hard. Oh wait, this is correct. Yeah, so it's 1 over 5 factorial. Where is this? For multiple events. Okay, I don't know what this principle, how this principle applies to multiple events. We have this. Huh, okay. I see. It's a bit hard. Okay. So you do this inclusion exclusion principle. You look at this formula. Some of these. Well, like, is there a simpler way to do this? I guess it's kind of hard. Oh my god. I want to go to distributions. It's really hard. We're almost done. How many people do we need in class to make the probability that? Well, if we're one person, if we're two people, it's 1 out of 360 times 1 out of 360. If you have 3 people, then you have, if you choose 2, well, generally if you have, right, because you look at the possible pairs, no, actually, sorry, I'm being stupid. For any given day, 1 out of 365. It'd be like 365 times 1 out of 360. You want n choose 2 times 1 over 365 is greater than 1/2, so then you have n factorial over n factorial over n factorial n minus 2 factorial. That's 365 greater than 1/2, so we have be like you just do that, right? Is my answer 23? Oh, my solution is wrong, huh? 19.6. So I got 20. I guess that's not quite right. You don't want to do n choose 2 exactly. this is not the right way to count. It's actually slightly higher. Because maybe you have like at least. Because you're treating them as independent events. But they're like. Okay. Sure. I see. Hmm. How is this a probability question? Oh, do you want me to use binomial theorem? Which we forgot. Yeah, I'm not doing that. That's not important. Okay, no, I don't care about this. Okay, conditional probability. Yeah, I think. Okay, so I've done this section. I think a lot of these problems were quite interesting, especially the counting ones where there's like a much better intuitive solution than me trying to brute force it. I think I still need some practice. So let's go like. Oh, okay. No, I want like brain teaser style questions. Yeah, let's just do this first. Sure. Okay, let's do these questions. I should be able to do them really quick. On a 6-sided die, each side has a number between 1 and 6. What's the probability of throwing a 3 or a 4? Each side has... Okay, there's 1 out of 3, no? Okay. 3 coins are tossed up in the air, 1 at a time. What is the probability that 2 of them will land heads up and 1 of them will land tails up? 1 over... No? Oh, 3 coins. Oh, okay. 2 of them will land heads up, and 1 of them will land tails up. Oh. One over 2 times 1 over 2 times 1 over 2 times, so 1 over 8 times 3 choose 2, right? 1 over 8 because that's a probability of like having heads, tails, and then order doesn't matter. So you just pick 2 of them to be tails, and then the other one will be heads automatically, right? That's what I think. Yeah, this is a wishy-washy answer. Like you fix, say it's heads, tails, and it can be any of the coins, right? So you just like 3 choose 2, which coins to go first and second. Out of these 3 coins, you're saying 3 choose 2. Like for this particular sequence, heads, tails, there's 1 over 8, and then you multiply it by 3 choose 2 because there are 3 choose 2 ways to assign these coins. So yes, I was just trying to confirm that this is my answer. 1 over 8 times 3 choose 2 is 3 over 8. Yep. Okay. Alright, good. I got it. A 2-digit number is chosen at random. What's the probability that the number is a multiple of 7? There's how many 2-digit numbers? 90, right? Yeah, there's 90, and then how many of those are multiples of 7? Okay, by the way, let's look at the... Oh yeah, let's answer this. What's the probability that's a multiple of 7? 7 times 2 is 14. And then 7 times... It goes from 2 to... 14, right? So 13 over 90. Okay. Cool. Okay, so how did they count this? Okay, I guess this is easier than what I did, which is 1 over 3 times, or 1 over 8 times 3 choose 2, which is 3. I guess that's kind of what I did, right? I just said, oh, there's... No, I just said, okay, the outcome, you just assume this, and how many ways are there to assign the coins, because you will not care about order in the end. So you can rearrange it afterwards, right? But you look at your coins and you assign them to one of these 2, and the third one will automatically be determined. Okay. How many will be red if... Okay. 14 blue, 6, okay. 425 buttons were red. Is now 1/3, which means... Okay, there's 20, 30 to 40. There's 15. So 5. One red was removed. Right, that's so easy. Okay, what's the probability of getting blue or red marble in the first draw? Or why is it not 9 over 14? Red or blue? Like, what, you just add them? Okay, I guess you have to do it fast. Has it a 6 on 6 on each 4 and 6? 1 over 6, bro. What do you mean? Okay. I see you know it was going to be aces in a row. 1 over 52 times 1 over 51. Sorry, wait, what am I saying? 4 over 52 times 3 over 51 times 2 over 50. 50 times 50 times 50. So let's say D. Because 50, yeah. Okay, next. Five over 15. 1 over 3. Both we play by, okay. 1 over 5 times 1 over 5. 1 in 25. This is too easy. Look, they are just from the bag. Just 10 over 62. 10 over 62 is 16%. Zero point wait, there are 2 winners. What's probably he's a winner? There are 2 winners. So you have to 2% chance of being like 2% times 100. Wait. Okay, my intuition was 0.2%, but oh, it's still 2%. I'm being stupid. Wait. If he buys 10, why is it not 2%? Okay, I guess like that's not what the question's asking. Like, you have 2 winners, so you have a 2%. So, like, the probably he isn't a winner is okay, this one I don't know actually. Like, each individual ticket has a 2% chance of winning. Is how you should think of it. And so if you buy 10 tickets and you're not a winner, it's like 1 minus 0.02 to the power of 10, right? And then 1 minus that. Okay. Alright, let's get back to this practice. Boys and girls. Because I really need to do, I think my weakness is like Bayesian inference, and when you look at VAEs and GANs, and a lot of this probability stuff is like really important to like be good at. Okay, oh wait, sorry, I'm not supposed to. Oh, like, so here, if like anyone is invited, then it's only 1 out of 4, right? But here it's actually P of A given B equals P of A and B over PB, where PB is the probability like like it should just be 1 out of 2. It's like my intuition, right? Because one of the children is a son, like the other children should be like it's either a boy or a girl, right? And you can't like count it. You need to assume with that loss of generality here, or like you just need to pick any one of the two children and their symmetry, and you cannot count it because of the symmetry. You cannot double count because there's symmetry, like the other children is automatically inferred. So it's 1 out of 2, but wow, is this like the Dorg thing? Which is why it's 1 out of 3. Oh, man. This is like the door thing, where if you switch it, your probability is 1/2. Is it the Monty Hall? Is it called the Monty Hall? Okay, this is why like the intuition is really important. I'm saying 1/2, but it should be 1/3. And okay, this makes sense, but you have to like intuit it. How do I intuit this? Yeah, like I'm not convinced that 3/4, like that's the probability of PB. Okay, let's ask chat, because like I need to figure out what's wrong with my logic. Help me intuit this problem. Basically, in my head, what I was thinking is like, okay, we can just assume, let's assume the first child is a boy. Then if we look at the second child, there's a 1 in 2 chance that it's a boy. So the answer is just 1 in 2. And I'm just trying to understand why that logic is flawed. Because the other way I'm thinking of it is like P of A and B over P of B, and P of A and B is simply like 1 over like both that you have, like it's 1 in 3, and then P of B is 1. Yeah, but the solution is saying like it's 3 over 4. Sorry, it's 1 over 4 and 3 over 4. I'm just a bit confused on like how we get these numbers. One point is this. Because yeah, it's fun. Like if you look at it, there are 4 outcomes, right? Boy, 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 girl, girl, boy, girl, girl, right? Now this doesn't exist. Girl, girl is in this world doesn't exist. You have 3. But if you fix boy, you have 2, right? But there's actually a world where the first, and I was trying to argue that there's symmetry, like order here doesn't matter. I guess the confusion for me is like, I always tell myself, okay, order doesn't matter. Like we can disregard whether it's the first boy or the second boy. Like if the first child or is the second child, like if we flip them, it doesn't matter. But I guess in this case, it does. Like in the coin problem, I was saying like 3 choose 2. Like, do you know what I'm saying? Oh man. Like, I was saying boy, girl, or girl, boy, doesn't matter. Why is my 2 choose 2 incorrect? How should I tell? Set 3 points, pick 2. my logic is kind of flawed. Yeah, I don't think the 3 choose 2 is exactly correct. Okay, there's another question where it was like, and I'm gonna explain to you my logic, and you help me correct it. It was asking like, what's the probability if we throw 3 coins that 2 of them are heads and 1 of them is tails? And what I did is like, I said, pick an arbitrary sequence like head, tail, head. That probability is 1/2 times 1/2 times 1/2, so 1/8. And then I'm saying, okay, how many ways can you assign the coins? You have 3 choose 2, so you get 3 choose 2 times 1/8, which is 3/8. And that was my answer, and that was the correct answer. But maybe that was not the right way to think about it, because the right way was like, okay, there are 8 possible outcomes, and only in 3 of those outcomes do you have like correct, like you have this constraint satisfied because you have 3 positions for t. But the way I'm counting it, like how you were assigning coins, like I'm not sure, like, I don't know how I got the right answer. Is you pick 2 coins that should be heads, right? So 3 choose 2. And it could be 3 choose 1, so 3 is the same thing. Choose a coin that should be tails, and then multiply that by the probability. Like how many ways? I was thinking of like how many different coins do you need to assign? Yeah, my logic can be a bit dangerous. Yeah, I failed to see that each outcome is equally likely. Yeah, it's the same. 1/3. What is the... goats. Stay with your original choice or switch. Like, yeah, it seems like it's one half, like, you actually have, if you don't switch, what's the probability that you're, it's actually 2/3, right, I think, but why is it 2/3, like, it just seems like it's one half and one half, but, like, if you draw the decision tree, it's correct, can you prove it mathematically? You have, like, P of, initially you have 1/3, and then there's a goat, so P of A given B is equal to MB over P of B. So there was 2/3 that the car and that B is a goat. Event A is A and B. I think, like, how do you calculate? Like, you can draw the decision tree as, like, the easiest way to do this. So initially you have 3 chances of, like, picking each. And if they show you that you pick door 1, you don't switch, you win. I forgot how to do this. Yeah, I think I was reading this. Okay, I have to go. I still need to get better at probability.